This program is brought to you by Stanford University. Please visit us at stanford.edu.
The question is, can you defeat the uncertainty principle in the following way? You measure the position of an object first to a poor accuracy. It's somewheres in here, somewheres within some region of size. Let's call it delta. And then you wait a long, long time, and the particle is someplace else, presumably, and you measure it again with the same poor accuracy. So it's over here, somewheres in delta again. How far did it move? The distance that, oh, and let's say we discover after having measured it that the center of these fuzzy regions, are separated by some distance, let's call it L. All right, so how well do we know the position? We know the position, or we know the separation. Let's talk about the separation. We know the separation is L plus or minus something of order delta. In other words, the distance of separation is L with a fuzziness or an uncertainty which is of order delta. 2 delta or a half delta, that's not the important thing. Now we want to find out how fast it was moving, so we divide it by the time. That's the amount of time between the two measurements. What's the uncertainty in the velocity? The uncertainty in the velocity is L over t plus or minus delta over t. And if we make t big enough, delta over t can be arbitrarily small. So it seems then that we can measure the position to accuracy delta, but the velocity to arbitrary accuracy, because delta over t gets smaller and smaller. Now the answer to this is, what we've done is we've measured, what we wanted to do was to measure the position and velocity at a time just before the measurement was done. We want to know, at a particular instant of time, right now, I want to try to measure the position and velocity sort of simultaneously. Or I want to know both position and velocity. Well, the problem here is that you don't know the velocity or the momentum as accurately as you thought, not if you meant the velocity before you measured, before you began the measurement. Before you began the measurement, the particle had a certain momentum. And then in order to measure it to within accuracy delta, you had to hit it with a photon of wavelength delta or smaller, and that in itself will change the velocity by an amount which is given by the uncertainty principle, h bar over delta. What you're doing here is you're measuring the velocity accurately, but the velocity after you made the first initial measurement of position. That velocity is a little bit different than the initial velocity, because in order to measure the position, you had to hit it with a photon. So you're not measuring what you wanted to measure, which was the original position and velocity simultaneously. You're measuring the position now to some accuracy, but then the velocity after you gave it a shot with the photon. So it's not what the uncertainty principle really talks about. Okay, let's, yeah.
How about on the other end?
Yeah.
You have now a particle of some velocity which you in fact are going to measure accurately. And at the end, you now know the location, the delta.
Yes, but you don't know the velocity anymore. Because
you know the velocity right before you hit it.
well, you don't know the velocity afterwards. So if you try to repeat the measurement of velocity to check it, you discover that it was a little different. It's a question of repeatability of experiments and checking your experiments. So you're always going to be stuck in that way that In any case, that is what the what the uncertainty principle says, is that you can't know in this case that the measurement of the final position over here will give a little bit of a kick to the velocity, and you won't know it afterwards. It says what it says, and you're perfectly right. I mean, there's something funny, but it says what it says, and what it says in this case is you can't check that that was the velocity without changing it by an amount of order h bar over delta. So you may think that that was the velocity. Okay. I think I measured it, but now you try to check it. And in classical physics, you can measure the position arbitrarily gently and not affect the velocity. In quantum mechanics, not so. Okay, so let's see. So are we ready to begin? Yeah, we're ready to begin. Okay. What I want to do before I do anything else is just an exceedingly quick review of complex numbers. Just not because I really want to teach you complex numbers. I presume everybody knows about complex numbers, but because just for some notational reasons. Incidentally, we're going to be continuing with linear vector spaces for a while. It's a somewhat dry subject. That's the bad news. The good news is it's a very easy subject. So once you get it, it should be easy enough. Thank you, Michael. But it does pay to spend a Michael, say hello to your mother. You're on TV. Okay. So let's just remind ourselves very quickly about some a property or two of complex numbers. Not all about complex numbers, just one or two properties that I want to remind you of, because we'll see things very similar to them later. Okay. Before we even do that, let me just mention about linear vector spaces. Linear vector spaces are composed of objects which you can multiply by numbers and add. You can add them and multiply them by numbers. And in fact, complex vector spaces are things that you can multiply by complex numbers and you can add them. That's what defines a complex vector space. The simplest complex vector space is, of course, just the complex numbers. The complex numbers, you can multiply them by other complex numbers and you can add them. So the complex numbers by themselves are a very simple linear vector space. I just want to tell you that, and then we can examine the complex numbers a little bit. A complex number is just two real numbers added together with I, x plus I, y. X is called the real part, y is called the imaginary part, and I is the square root of -1. All arithmetic, or let's call it algebra, all elementary algebra, multiplication of complex numbers, addition of complex numbers, is exactly the same as if they were ordinary numbers, except you must remember that I squared is -1. That's all. That's the theory of complex numbers in a nutshell. Every complex number can be represented as a point on the xy plane. Don't confuse this xy plane with any vector space. It's just the xy plane. So every point in the complex plane has an x and a y, and it can be plotted. And it's usual to call it z. It's a common terminology for complex numbers. If we wanted to remember that complex numbers are vector spaces, that they can be added, and use the notation that we started to use last time for vector spaces, namely that a vector in a vector space is often represented in quantum mechanics, in any case, in a complex vector space, by a ket vector, just a symbol, Dirac's famous symbol that looks like this, then we might just say the complex numbers are very, very simple vectors in a simple vector space. In fact, as we'll see, it's just a one-dimensional vector space. as we'll see. Complex numbers, just in the same sense that the real numbers can be thought of as vectors on a line in one dimension. The complex numbers are a complex vector space of one dimension. We'll find out eventually what dimension means, but for the moment, let's just not worry about that. Now, every complex number has associated with it a complex conjugate. The complex conjugate is usually represented by putting a star over it, and it's just the same real part minus iy. And so what it is it's the reflection, this is z, it's the reflection of, as if the horizontal axis was a mirror. Just the reflection about the x-axis, that's called z star. Another way that we could represent it, if we were using the notation of complex vector spaces, would be that way. This is called the bra vector. This is called the ket vector. When you put one next to another, it's called a bracket or a bracket. Really, the bra vectors are really basically just complex conjugates of the ket vectors. So if we were just dealing with a one-dimensional vector space, complex vector space, just the complex numbers, we might easily use the notation z and z star, or ket z and bra z, and they would mean essentially the same thing. Okay, let me just point out one more important property that we will use, and we'll use the analog of it for vector spaces. The reason I'm doing this now is to do something in a very simple context that we'll do over in more complicated contexts. Supposing I have two complex numbers, z1 and z2, and I multiply them together. Let's just do it over here quickly. z1 is x1 plus iy1. z2 is x2 plus iy2. Thank you. All right. We multiply these together just to do it once. It's x1, x and y are both real. x1 times x2 is x1, x2. That's real. We have also another term in the real part that's y1 times y2, but it has a minus sign because I times I is minus 1. So that's minus y1, y2. This is the real part of the product. And then there's the imaginary part plus I. And what multiplies I gets multiplied by x1, y2 plus y1, x2. x1, y2 plus x2, y1. All right, so here we would take the product and separate it into a real and imaginary part, and that defines for us the real and imaginary part of the product. A very simple theorem. This theorem, it's hardly a theorem, it's just a little exercise. The complex conjugate of a product, how do you get it? What you do is you just change each plus I to minus I. Okay? Each plus I becomes minus I. That gives you the complex conjugates of z1 and z2. And what will it do? You'll work your way through this, and it will just change the I over here, nothing else. The simple lemma, theorem, whatever it is just that the complex conjugate of z1, z2 is just z1 star, z2 star. In other words, you multiply the complex conjugates. Just for notational reasons, I'm going to change the order here and put the 2 here and the 1 here. Oh, another example, another similar fact. What about z1 star z2? Supposing I take z1 star z2, that's a thing I can write down, and I take its complex conjugate, the complex conjugate of this product. The rule is just complex conjugate each factor, and that's just equal to z2 times z1 star. So when you complex conjugate a product, you just complex conjugate. Did I write it right? No. That should just, yeah, thank you. Z2 star Z1. Sure it is, but I don't want to do that now. Yeah. Another way to write it, to write the same thing, which generalizes to vector spaces, to more complicated vector spaces, is that if I have two complex vectors, let's call them, instead of calling them by the notation Z now, let's just call them A and B. All right, the rule here is now think of the B's as being complex conjugates because they're bra vectors, and A's as being the original vector space because they're ket vectors. All right. Well, the rule that is analogous to this is that if we interchange, here, look at this for a moment. Supposing we interchange Z1 and Z2, what happens to the result? If we interchange Z1 and Z2, let's do it right here. The interchange, this is the interchange operation. The interchange operation will turn this into Z1 star Z2. Just interchanging 1 and 2. Just interchanging 1 and 2 will replace Z2 by Z1 and Z1 by Z2. But this is just a complex conjugate of this. So interchanging the 1 and 2, or the bras and the kets, just does nothing but complex conjugates. So, to make it short, if I take if I take some sort of product, we haven't defined this yet, but I'm just writing it down for future reference. If I think of complex numbers as vectors in a vector space, and I multiply the bras times the kets, which means multiply the complex numbers by their complex conjugates, then you just interchange the two complex numbers and complex conjugate. So when you interchange the bras and kets, it's equivalent to complex conjugation. We'll come back to it in some detail very shortly. It's just a useful thing to keep in mind that the mapping from bras to kets is essentially complex conjugation. Okay, let's go back and very briefly, quickly review what a complex vector space is. As I said, it is really the heart of the mathematics of quantum mechanics, and we can't do without it, so we have to spend a little bit of time. First of all, it has a set of elements called A, B, C, and so forth. How many of them? An infinite number of them, but as we'll see, infinite in a certain sense. Just like the complex numbers, there are an infinite number of complex numbers. There's also an infinite number of elements that we're going to call A. And they have the property that, first of all, you can multiply any one of them by a complex number, alpha, and you get a new one. Let's call it C. So multiplication by a complex number is a allowed operation that gives you another vector, and adding them, A plus B, is another allowable operation. You can put these two together, and you can say, given any two vectors, any two complex vectors, you can add them alpha A plus beta B and get another complex number. If you can multiply them by complex numbers, and if you can add them, then you can add them in combination with coefficients in front of them. And the point is that they're closed under these operations. See, alphas and betas can be any complex numbers. Now, for example, this would preclude the real numbers as being a complex vector space. The real numbers cannot be multiplied by complex numbers and give back real numbers. So the real numbers are not a complex vector space. They are a real vector space. meaning to say that the real numbers can be multiplied, they can be multiplied by other real numbers, real constants, and they can be added. So they're a real vector space. But what about the positive numbers? Are the positive numbers a vector space under the reals? No, because part of the definition of a real vector space is that you can multiply numbers by any real number, positive or negative. So, and that's it. That is the definition of a complex vector space. Let me give you two examples. We talked about them last time, just to review them very quickly. One example, ordinary vectors are vectors, form a vector space, and they form a vector space which is a real vector space. Ordinary vectors, which are just arrows in space, can be multiplied and added, but multiplied only by real numbers. It does not make sense to take an ordinary vector, my finger, and multiply it by a complex number. All right, so ordinary vectors are a vector space, but they're a real vector space. All right, some examples of complex vector spaces. Complex functions. Let's call it psi. A function of a variable. Now, the variable does not have to be complex. It can be complex, but it doesn't have to be complex. It could just be an ordinary real argument of the function. Argument means the thing that the function depends on. Psi of x, where x is real, but psi is complex. In other words, psi is of the form some real part, let's call it psi real of x, plus I times psi imaginary of x. That's the collection of complex functions of a real variable, for example. Okay? These form a vector space. Why? You can multiply them by numbers and you get new functions. You can multiply them by complex numbers. If I take a complex function, psi of x, and multiply it by any complex number, say alpha, I get a new complex function, number one. Number two, I can add complex functions. Two psi, a psi and a phi, for example. Psi of x plus phi of x gives me another complex function. So they form a complex vector space. Now, we're not used to thinking, unless you've been doing this for some time, you may not be used to thinking of functions as vectors, but they are vectors in this mathematical sense. Okay. Another example that we'll use over and over are column vectors. Column vectors are really functions also. They're functions of a discrete index. A discrete index, instead of a continuous x, they're functions perhaps of an integer, but maybe an integer that only goes from 1 to 4, or 1 to 3, or 1 to 7. And we can represent them by a column. I'm going to use, for these discrete kind of vectors, I'm going to use a's and little b's, little a's and little b's. But if I put the entries into the column A1, A2, A3, these are just numbers now, complex numbers. A4, for example. The set of column objects like this with only 4 complex entries forms a vector space. You can add 2 of them by the following operation. Let's call it B1, B2, dot, dot. And define. This is definition of adding them. A1 plus B1, A2 plus B2, A3 plus B3, A4 plus B4, and so on. You can also multiply them by constants. If I want to multiply the vector A by a constant, let's call that constant alpha again, all I do is multiply the entries by alpha. Each entry gets multiplied by alpha. And so alpha times a column vector is just a column vector by definition, which is alpha A1, alpha A2, dot, dot, dot. So you can multiply them by constants. It's kind of obvious that this notation here is describing components of a vector. We could, in fact, think of these entries here as kind of like the components of a vector. If I were to give you an ordinary vector in space, let's say three-dimensional space, I could describe that vector by three components, x, y, and z. And if I liked, if I wanted to, I could exhibit those components in the form x, y, and z. But of course, now I would be talking about a real vector space, and the x, y's, and z's would be real. So there's nothing terribly unusual about what I'm doing here. You can also think of these objects as functions of the index. If I tell you which index, if I tell you I'm talking about 3, then a of 3 would be a function, well, it would be a function of a discrete variable which goes from 1 to 4 here. So in that sense, even these discrete vectors can be thought of as functions, not continuous functions, but just functions with whose independent variable just takes on 4 values, 1, 2, 3, and 4. Okay. Now, what about the dimension of a vector space? The dimension of a vector space can be defined as follows. You can define it as the minimum number of vectors that you need so that you can write any vector as a sum with coefficients of that minimum number. All right? Let me give you an example. Let's take a one-dimensional vector space, just the ordinary line. Okay? And we can think of vectors on the line. Vectors on the line are just, of course, real numbers, but I could represent them as arrows from 0 to some real number. If I'm allowed to multiply this vector, this could be a unit vector, or it doesn't have to be a unit vector, but if I'm allowed to multiply this vector by any real number, let's call it r, and let's call this the vector v, then I can, and r can be positive or negative, then I can get any vector out of it. So it only takes one vector to get started and to be able to represent any vector by, in this case, just multiplying it by a constant. Now, let's go to a two-dimensional vector space. A two-dimensional vector space, and I'm thinking now about real vectors just so we can draw it on the blackboard. The blackboard is a two-dimensional vector space. If I give you any two vectors which happen not to lie on the same line, if I give you any two vectors which happen not to lie on the same line, then by multiplying this vector, let's call this v1, let's call this v2, by multiplying v1 by a constant, r1, let's say, times v1, plus r2 times v2, I can generate any vector in the plane. All I need is two vectors. I could draw another vector in here, v3, but I don't need it in order to represent any vector by summing up multiples of v1 and v2. I don't need it. It's redundant. In fact, v3 itself can be expressed in terms of v1 and v2. v1 and v2 can be added with appropriate coefficients to get v3. So the question is, how many vectors do you need? What's the minimum number of vectors that you need in order to be able to add them up with coefficients and generate any vector in the vector space? That minimum number is the dimensionality of the space. In this case, it's 2. If you had a three-dimensional vector space, for example, you could generate any vector by taking 3 vectors along the mutually perpendicular axes, or any other 3 vectors as long as they don't lie in a plane. as long as they don't lie in a plane. So it takes three vectors in order, a minimum of three vectors in order to be able to represent any vector lying in a three-dimensional vector space. And that's the general definition. How many vectors do you need in order to be able to add them up with coefficients and represent any vector in the space? Let's look at some examples. How many vectors do you need? Let's take, here we have vectors, column vectors made with 4 entries, only 4 entries. I assert that that's a 4-dimensional vector space. How do I see that? Well, there are 4 vectors, and you need all of them, incidentally. Any fewer than this, you wouldn't be able to represent any vector. But you can take the 4 vectors to be 1, 0, 0, 0, comma, 0, 1, 0, 0, 0, 0, 1, 0, and of course the last one is 0, 0, 0, 1. If you add up these vectors with coefficients a1 plus a2 plus a3 plus a4, then what do you get? You just get the vector a1, a2, a3, a4. The first one will give you the vector a1, 0, 0, 0. The next one will give you the vector 0, a2, and so forth. And when you add them up, you'll get back to this vector. So the conclusion is that you need, oh, incidentally, if you threw away one of these vectors, then you would never be able to construct vectors. There would be vectors that you couldn't construct in this way. Okay? In particular, let's suppose we threw this one away over here. Then we'd never be able to get a vector which had something in the bottom entry here. So you need all 4 of them, but that's all you need. You don't need a 5th vector in order to be able to write down every vector as a sum in this way. So a column vector space composed of 4 entries is 4-dimensional, and so on. 5 entries would be 5-dimensional, 2 entries would be 2-dimensional. What about just 1 entry? 1 entry would be just the good old complex numbers. It would be a 1-dimensional vector space. So a column vector with just 1 entry is just a number. It's just a complex number. And they form the 1-dimensional vector space, complex vector space. All right, so let's just summarize that by saying, oh, what about the functions? What about the functions? Let's say the continuous smooth functions on a line. How many functions does it take to be able to write every function as a sum? An infinite number, obviously an infinite number. There's no finite set of functions that you can add up with coefficients that will generate every function. If I have a few functions, that one, this one, a couple of others, it's rather limited what I can generate by adding them up with coefficients. In particular, I'll never generate a function which looks like this. So you need an infinite number of functions in order to be able to write all functions. Now, all functions is a huge number of things, all continuous, differentiable, smooth functions. You still need an infinite number of them. I won't try to tell you how big that infinity is, but you need an infinite number. And so for that reason, the functions are called an infinite dimensional vector space. But you can think of it simply as a vector space with an infinite number of axes. It's a little mind-boggling. I suggest you don't try to think about it that way. Okay, so there we are. We have functions. Psi of x. And we can think of them, this symbol means think of them as. We can think of them as vectors in a complex vector space. Phi of x is another vector. These are 2 different vectors, and they form an infinite dimensional vector space. In the same way, the column vectors A1 dot dot, let's say 6 this time, a 6-dimensional vector space, can be thought of as the vector A. The vector A, which is determined by the 6 small letters A1 through A6. All right, so that's the notation that we'll use to describe vectors. And typically, vectors are closely related to functions, either of continuous variables or discrete variables. Now we come to the idea of the dual vector space. The dual vector space is really just the complex conjugate vector space. That's a secret that mathematicians don't let out. Well, for good reasons. It's not arbitrary. When they want to be general and they want to be rigorous, they prefer not to think of the dual vector space as being limited to just complex conjugation. You can have other kinds of operations. But for us in physics and in quantum mechanics, basically the dual vector space means the complex conjugates. And we think of the complex conjugates as forming a separate vector space, a different one, but related. So, just like for every complex number, we have its reflection. If the complex number is in the upper half plane, then its reflection is in the lower half plane. If the complex number is in the lower half plane, then its reflection is in the upper half plane. We actually have a pair of redundant descriptions of the same plane, one in terms of the complex numbers, and the other in terms of the complex conjugates. It's really the same plane, but we think of them as 2 different vector spaces. But there's a mapping between them. For every complex number, there is a complex conjugate. For every ket vector z, there is a bra vector z, its complex conjugate. And so we think of a vector space coming together with a second vector space, which is in a certain sense identical to it, or isomorphic to it, contains the same, well, I won't say it contains the same object. That would be wrong. But they're in one-to-one correspondence. But let's suppose now, and they're labeled, if A is a vector in the ket space, then A, with its arrow facing in the other direction, is essentially its complex conjugate. What does that mean? Well, for example, if the vector space is the space of functions, then the dual vector space is simply the things made up out of the complex conjugates of the functions. There's a mapping between them. For every A, there is, for every ket vector, there is a bra vector. Just as for every complex number, there is its complex conjugate. So one example of this is the mapping of between complex conjugates. Well, it's always a mapping between complex conjugates. But if we were talking about column vectors, then the usual notation, now some of these things are just notations. You can't ask me why, because it's just a notation. Turns out to be convenient. If you represent the original ket vectors by a column, then the bra vectors are represented by a row. It's nice to keep track of which are the bras and which are the kets by making the kets be columns and the bras be rows. But the entry to the rows are the complex conjugate numbers. That's the important thing. All right, so for every column vector, you have the complex conjugate row vector, and those form the bras and the kets. This can be thought of as the bra vector. This can be thought of as the ket vector. Notice we don't put a star in here. The star is indicated simply by drawing the ket vector instead of the original vector. So think of ket as being a symbol for complex conjugation. All right, now, supposing we have two vectors, not two vectors, we have a vector A and its image in the dual vector space. We have the vector A, it's bra, no, it's ket, and we have its image in the dual space, which is the bra. Now supposing we multiply A by the complex number alpha. What is the image of that? You might think that it's just alpha times A. What's wrong with that? You want to conjugate it because you want the bra vector associated with alpha A to be the complex conjugate of the ket vector, and that entails complex conjugating the number that you multiply A by. So you really want to put a star here, alpha star. Complex conjugating, this is just a statement that complex conjugating a product requires you to complex conjugate both pieces of the product. Okay? We had, where was it? Yes, here it is right here. Complex conjugating a product means complex conjugating both factors. So the complex conjugate of alpha times A, if A was just a number, for example, would be the complex conjugate of A times the complex conjugate of alpha. Notice that when I'm speaking about simple numbers, I won't use the notation of vector spaces. I'll just use the complex conjugation. So when thinking about vectors, we complex conjugate them by turning them from bras to kets. When thinking of them as the coefficients, just the numerical coefficients, we'll use the notation of complex conjugation, star. All right, so keep that in mind, that the dual vector space, when you multiply a vector by a constant, the image in the dual vector space gets multiplied by the complex conjugate. Otherwise, operations on the dual space are similar to operations on the original space. For example, if A and B are two vectors, and we add them, then the dual, or the complex conjugate, will just be the sums of the dual vectors. That's a lot of information, and it pretty much allows you to reconstruct the dual vector space. As I said, for example, the dual vector space to the space of function. Yeah, good.
Is there any significance to putting the alpha star on the right?
No, there's no significance to it, no. There's sort of a tradition of keeping your formulas neat by writing them a certain way. But in this case, no, there is no significance to that. That's a good question. Other times there will be. For other objects there will be. When we multiply vectors by operators, then it does matter where we put them. But when it's just numbers, no, there's no significance. But I try to keep things neat by following a certain pattern. But you don't need to worry about my pattern. Okay, that's the basic idea of linear vector spaces and their duals. Or their conjugates. Next, the next construction that you have to keep track of is the inner product between two vectors. The inner product is the analog in ordinary vector dot products. Just remind you very quickly what the dot product of two vectors is, ordinary vectors. You take the two vectors. You can think of it in a variety of ways. You can think of it as take the projection of one vector onto the other, take the magnitude of that projection, let's call this B, let's call the original vector A. This distance here is the projection of B onto the axis of A. If we multiply the projection of B by the magnitude of A, that gives us one form of the dot product. We can do it the other way. We can take the projection of A on B and multiply the length of the projections. The symmetric way to write it is that it's A times B times what? Cosine of the angle between them. But if we write it in terms of components, let's suppose we write it in terms of components, the components, for example, along any set of axes, any set of orthogonal axes, the x and y axis, for example, then if we know the components of A, let's say AX and AY, that's A, and BX and BY, then the dot product of A and B is just AX BX plus AY BY. So we ordinarily write that for ordinary vectors, now, I just mean little pointers. A dot B is equal to AX BX plus AY BY. What if there's a third direction? Straightforward. If there's a third direction or a fourth or a fifth or a sixth direction, you just keep going. AZ BZ. So in other words, it's just the sum of the product of the components axis by axis, x, y, z, and so forth. In parallel, or not parallel, or in analogy with this, we invent the generalized idea of the inner product of two vectors. Let's call them capital A and capital B. And we write it as A times B. Now, this is the inner product of the ket vector B with the bra vector A. Because we were dealing with real vector spaces, we didn't have to worry about complex conjugating anything. But when we're dealing with complex vector spaces, when we multiply two vectors, we have to decide which one is the ket vector and which one is the bra vector. Once we do that, then I'll tell you what the rule is. First of all, the inner product has some properties. This is abstract. First of all, it has some abstract properties. The first abstract property is supposing you multiply the vector B by beta. So this is beta times B. This is the inner product of A with the vector beta times B. So let's put all of this in a parenthesis here. Parentheses. That inner product is just beta times the inner product of AB. If you double, in other words, if you double the length of B and not double the length of A, then you just double the inner product. Okay? If you were to double both A and B, of course, you get a factor of 4, but we're just doubling or multiplying by beta one of the vectors. If we do that, then the inner product itself just gets multiplied by beta. Another fact is that if we multiply A by a sum, let's say B plus C, the inner product of A with B plus C. That's just given by A inner product with B plus A inner product with C. The mathematical language is that the inner product is linear, is a linear operation on B. These are all properties that ordinary dot products between vectors have, and they're properties that you can check for the inner products between more abstract vectors if I give you the rule. So far I haven't given you the rule for inner products for column vectors or for functions. I'm going to give you that as examples. But before I do, I want to finish up with the abstract properties. Another abstract property is that the inner product of A with B, ket vector B, bra vector A, is related to, but is not equal to in general, the inner product of B with A. Notice what I've done here. Effectively, I've complex conjugated both A and B. I've replaced A by the complex conjugate of B and B by the complex conjugate of A. What would you get? What would you expect to get on the right-hand side here? Now, if you take two numbers and you multiply them, sorry, if you take a number times, you know what I mean. You've complex conjugated both factors, you can expect that the result is just the complex conjugation. So that's the correct equation. When you interchange bra and ket vector, you have to complex conjugate. And that's the rule for, that's analogous to a rule, let's see, it's analogous to this one. Z1 star times Z2 star is Z1 star Z2. Okay, you see what I've done. Yeah, I think it's the first one. Right. Okay, so if you complex conjugate both factors, then the product complex conjugates. This is now to be taken as an abstract part of the definition of a good inner product. The last definition, from this we can derive something very simply. Supposing we take the inner product of a vector with itself. Then this says that it's equal to the inner product of the vector with itself. If I interchange A and A, that doesn't do anything. Complex conjugated. So it says that whatever this object is, whatever this number is, or the inner product is incidentally a number, not a vector. The inner product is a number. The inner product of A with A is its own complex conjugate. What are numbers called which are their own complex conjugates? They're called real. Right? They're numbers on the real axis. They're their own complex conjugates, so they're their own reflections, and that means they're on the real axis. So the inner product of a vector with itself is real. Now, there's one more property that the inner product actually inherits from the complex conjugation idea. Again, it has to do with the complex conjugate of a thing with itself, or an A with an A. What do we know about the complex conjugate of a, what do we know about the product of a complex number with its conjugate, besides the fact that it's real? It's positive. It's positive. It's always positive. Let's just check it. It's x plus iy times x minus iy. The imaginary part cancels. Ix, both terms have an xy times an I, but one has a plus sign, the other has a minus sign. But then this is equal to x squared plus y squared. Plus y squared because I times minus I is plus 1. Okay, so it's always positive, x squared plus y squared. Real and positive. This is part, or in fact, this set of requirements that when you multiply a bra vector, or ket vector by a complex number, that simply multiplies the inner product by the same number. You can take inner products with sums, and you just get the sum of inner products. When you interchange bra and ket, you complex conjugate. And one more rule, that the inner product of a vector with itself is positive. That it's real follows from the previous one. It doesn't follow from anything. It doesn't follow from anything. As an example of where it doesn't follow, in real vector spaces, 4 vectors in relativity can have inner products with themselves which are positive or negative or 0, light-like, space-like, and time-like. So it doesn't follow from anything, but it is part of the definition of an inner product in a complex vector space. All right, so what is a... these are rules about what the inner product has to satisfy. Now, you may be able to find more than one construction for an inner product which is consistent with these rules, and in general you can. But I'll give you the simple inner product for functions and for column vectors which satisfies these rules very easily. And I'll leave it for you to go home and prove the various properties, these 4 properties here. You do it by inspection, it's not very hard. For a function, or for the vector space of functions, the inner product of phi with psi, phi and psi are both functions, phi of x and psi of x, right? That's equal to the integral dx. Now, of course, you have to decide functions over what interval, for example. We could have functions on the interval from 0 to 1. We could have functions from minus infinity to plus infinity. But whatever the interval is here, integral of phi star of x, psi of x. Notice that because phi is the bra vector, it gets conjugated in here. And we just multiply phi star of x by psi of x and integrate. Right? Easy, very, very straightforward to prove all of these properties here. I'll leave it to you as I said. So that's the inner product, or the dot product, between 2 functions. The integral phi star psi. For column vectors and row vectors, the bra vectors, let's call the bra vector B1, B2, B3, 3-dimensional complex vector space. And let's take the row vector, no, sorry, this is the row vector. Let's take the column vector, the ket vector, to be A1, A2, and A3. And I'm sorry, I should have put complex conjugates here. The entries to the row vector are complex conjugates. Then the inner product between B and A is just, in very close analogy, I think we've lost it off the blackboard, but in very close analogy with the way you take inner products for ordinary vectors, it's just the sum of the products of the components. B1 star A1 plus B2 star A2 plus B3 star A3, dot, 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 however many of them there are. Yes?
But the coordinates of the vector B are still plain old B1, B2, B3.
The coordinates of the ket vector B are B1, B2, B3. The entries into the bra vector are the stars. Now, I think what you're saying is we would normally call this vector A, and we would call this one just plain B. We wouldn't put a star there. That's a notational, traditional notation. The star is indicated by the backward arrow here. But the components of it really are the complex conjugates. Okay, so that's the idea of an inner product. All right, let me stop now for questions because I'm going pretty fast. Questions? Yes.
So the X in there really has to be real.
Oh, here. Well, yeah, right. But we could, yes, but we could, for example, have more than one argument in here. So it could be x and y, and then we would integrate dx dy.
Yeah, but then they both need to be real.
They're both real, assuming they're both real. Now, a function of 2 variables can be thought of as a function of a complex variable, but let's not do that. Let's think of the arguments as real. I think we're better off. In most situations, we will want to do that. All right, now, shall we take a break for 6.5 minutes? All right, now I want to come to the concept of a set of basis vectors For ordinary vector spaces, let's say two-dimensional vector spaces on the blackboard, basis vectors are just a pair of unit vectors pointing in orthogonal directions, which can be chosen somewhat arbitrarily, not completely arbitrarily. You pick one unit vector and then pick the other unit vector being perpendicular to it. For most purposes, it's usually convenient to draw the basis vectors on the blackboard so that they're horizontal and vertical. And they're just simply vectors that are useful in writing any vector in terms of them or in taking components of vectors. And let's define a basis set the following way. First of all, they're unit vectors. Unit vectors means that their inner product with themselves is 1. The dot product with themselves is 1. Incidentally, for ordinary vector spaces, the dot product, just real vector spaces, the dot product is just the square of the length of the vector, of course. So that's why it's always positive, among other things. The square of the length of a unit vector is 1. So, first of all, let's imagine in our vector space a collection of vectors which I will call, what shall I call them? I guess I'll just call them B for basis. Little b now. Now the little b's are not numbers now. They're a collection of vectors. B sub I. How many of them are there? The number is equal to the dimensionality of the vector space. So if it's a 7-dimensional vector space, there are 7 B's. I equals 1 through the dimension of the vector space, D for dimension. Okay? B1, B2, B3, B4. Now, they're not what shall I say, uniquely fixed, but they satisfy some unique set of assumptions. The unique set of assumptions is, first of all, that they're unit vectors. That says that every B, the inner product with itself, this is not summed over now. Often I use the notation that when you sum over, or when you repeat an index, you sum over it. Here I do not mean the sum, no sum. Just take the ith vector, take its inner product with itself. That's assumed to be 1. All right, so every one of these B's, every one of these vectors B, B1, B2, and so forth, have unit length. Next, they're perpendicular to each other. What does it mean to be perpendicular to each other? For ordinary vectors, it means that the dot product is 0. When two vectors are perpendicular, remember that the dot product is the projection of one onto the other. If they're perpendicular, there is no projection. So let's write it this way. Yeah, okay, that's fine. If I take two different vectors, let's say B1 and B2, or BI and BJ, for j not equal to I, j not equal to I, then that's 0. That's the assumption that they're orthogonal. A vector of unit length is called normalized, or normal. A normal vector is unit length. A set of vectors which are mutually orthogonal to each other are called mutually orthogonal to each other. If they're both normalized and orthogonal, they're called an orthonormal collection of vectors. Orthonormal collection of vectors. And if there are d of them, then they're a basis. They're a basis of vectors for the vector space. We'll see what that means in a moment. It means you can easily expand any vector in terms of them. Let me give you an example. Just in terms of column vectors, I've already given you the example. 1, 0, 0, 0. There's nothing special about 4 dimensions here. I've just chosen 4-dimensional vector spaces for 0, 1, 0, 0. This could be B1. Let's write it out. the vector B1 is to be identified with the column 1, 0, 0, 0. And I'll write down the fourth one, and you can fill in the other two in between. B4 is to be identified with 0, 0, 0, 1. Each one is of unit length. That's obvious because each one has only one entry, and when you calculate the inner product with itself, each one has only one term in the inner product, and it's just 1 times 1. Right? The inner product between any two of them will always be 0 because they don't have entries in the same place. For example, the inner product of this one with this one will be 0. It's 1 times 0 plus 0 times 0 plus 0 times 0 plus 0 times 1. So this is an orthonormal basis of vectors for a simple 4-dimensional column vectors. This is not the only orthonormal basis. You can find, just in the same way as I could choose these two vectors to form a basis on the blackboard, I could also choose these two vectors to form a basis on the blackboard. They're supposed to be unit vectors. So there's a degree of ambiguity in the basis, but you can check a given set of vectors and check whether it's a basis or not by calculating their inner products. Yes?
The inner product of a bra with a ket, but you look like you're doing the inner product of 2 kets.
Where?
Right here. So you wrote down 2 ket vectors.
Oh, yeah. Okay, that's right. Yes, 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 yes. No, no, you're right. Let's straighten that out. I should have written B4, and I should have written that this is equal to the row vector 0, 0, 0, 1. Does that help? Good. Yeah, no, that's a good point. Just for consistency, I really should have written B1 as a ket vector, B4 as a bra vector, and then taken the inner product of B1 with B4. Good. I was jumping ahead a little too quickly. All right, this equation now, these two equations can be summarized by a single equation. This is bi bj if j is not equal to I. If it is equal to I, then the answer is just 1. So bi bj is equal to 1 if I is equal to j. It's 0 if I is not equal to j. That's the Kronecker delta symbol ij, delta ij. Delta ij is defined so that it's 1 when I is equal to j and 0 when I is not equal to j. That's the definition of the Kronecker delta, and that defines a basis. Now, let me show you how to take any vector. Let's suppose we have d basis vectors. We know we don't need more than d vectors in a d-dimensional vector space in order to expand any vector. That's the definition of the dimensionality of the vector space, that you don't need more than d vectors. We have d vectors, namely the d basis vectors. Therefore, it should be possible to take any vector, let's call it v, any vector, and write it as a sum over the basis vectors of coefficients, and let's call those coefficients vi, times the ith basis vector. And this is just, you know, v1, b1 plus v2, b2, and so forth, etc. All right, now let me take the inner product of both sides of this with some particular one of the b's. I could call it bj, but let me do it very extremely specifically. Let me take the inner product of this with b1, all right, with the first basis vector. b1 with v. What do we get? Well, we get a sum over I of the inner product of B1 with this expression. But that's just VI B1 BI. Notice, it's summed over I, but I've chosen the first basis vector on the left here. So one of the indices is just 1. I don't want to confuse this with I. Let's draw it so that it looks like a 1. Does that look like a 1? I hope so. Okay. Now what is this thing? It's summed on I, but there's only one term in that sum. That's because B1 is orthogonal to all the BI's except for I equals 1. Okay? So there's only one term, and that term is when I is equal to 1. When I is equal to 1, the inner product here is just the number 1. So the result is just V1. What about the inner product of B2 with V? Exactly the same argument will tell you that the inner product of B2 with V is the coefficient V2. Now this is kind of interesting. I have now figured out what the V's are. If I give you a vector V and I ask you to expand it in terms of the basis vectors, it's very easy to figure out what the coefficients are. The coefficients are just the inner products of V with the basis vectors. So we can now write a more general formula and put it together. Let's write a more general formula, put it together. First of all, we can say that, let's call it Bj V is Vj. Now I want you to imagine that Vj was the thing I was trying to figure out. I was trying to figure out what expansion coefficients I need here in order to expand the vector V. I want to write V in this form. Right? Well, the answer is that the expansion coefficients are just these inner products. But now let's rewrite this equation. I can also write, of course, that Bi V is Vi. Doesn't matter whether I stick J or I there, same formula. And now let's rewrite this formula here, sticking in the V's that I've calculated. So let's do that. We have V is equal to a sum. Now I'm going to start by writing Bi here. You asked me earlier whether there's any significance to whether I put the Vi on this side or on that side. The answer was no. So I'm going to choose to write it over here. But now I'm going to take what Vi is, namely the inner product of Bi with V. So let me just substitute that in. Bi with V. That's a kind of neat formula. That formula will come up over and over again, sort of easy to remember. V is the sum over all the basis vectors of the ith basis vector times BIV. And I choose to write it in this form because later on when we find out what an outer product of two vectors is, we'll discover that this has some nice significance. But this is a formula for any vector if you know its inner product with the basis vectors. Okay, so that's a useful formula. Which we will draw on over and over again. But for the moment, that's it about vector spaces. We haven't discussed operators yet. I don't know if we'll have time tonight. I would like to get to operators. I think we will. But let's just talk a little bit now about the physical significance of vector spaces. In classical mechanics, the space of states, the phase space, the space or the collection of possible configurations of a system form a set in the mathematical sense of set theory. The operations that you can do with sets are the usual operations that you can do. You can form the intersection of two sets. That's the operation. That's the operation of AND. Now, if you have a set, if you have a set of some kind, and you consider some subset, and you consider another subset, then the things which are in both subsets are the intersection, and the things which are in one set or the other set are the union of the two sets. Those are the basic operations, or two of the fundamental operations of set theory, intersection and union, and they correspond to and or. Okay. Quantum mechanics is very, very different. The concepts of and or are quite different. We're not going to talk about them tonight, but the difference derives from the fact that the states of a system are not points in a set, they are vectors in a vector space. And the algebra of vectors is very different than the algebra of Boolean algebra. Boolean algebra being the algebra of ordinary sets, of ordinary set theory. So what is the connection between states and vectors in quantum mechanics? Well, let's go back to what we discussed last quarter. Let's start with some discrete systems. The coin. The coin was a good system that was useful for us in formulating classical logic. The coin had two states. The coin on the table. I don't have a coin. Do I have a coin? Yeah. It's a penny. Okay. Coin can be heads or tails. It came up heads. And so heads or tails, the coin is a two-state system. The classical coin is described by a system with two states, heads and tails, and they form a set. That set is called the phase space. We discussed this extensively last quarter. I'm not going to discuss it again. We could also think of this slightly differently. We could think of the coin as having an arrow, a pointer embedded in it. And I don't want to call this, I'm not going to call this a vector on purpose. I'm going to call it a pointer, just to distinguish it from the vectors which describe vector spaces of states. We'll call it a pointer. It points in some direction. And here, the pointer is pointing up. Here, the pointer is pointing down. And I could call these two states either up and down, heads and tails, or I could even give them a different name. I could call this state plus, or even +1 and -1. Just giving them names now. We would call these states +1 and -1. In quantum mechanics, we take these two states of the coin, but of course we don't really need quantum mechanics for coins. It wouldn't do us very much good. But for some very, very quantum mechanical variable, which could either for one reason or another be up or down, I'm really thinking about the spin of an electron, but for the moment it's just a system which can take on two values and only two values, either heads or tails, +1, -1, or up or down. Okay. And we simply assign vectors to these two states. Two basis vectors, two orthogonal vectors. One of them we can call heads, the other one we can call tails, or we can call them the vector +1 and the vector -1. Now these are just names. This +1 doesn't mean that this vector has length +1, and it doesn't mean that this vector has length -1. They're just names. The vector +1 and the vector -1, or if you like, the vector heads and tails. Okay. Well, you could do this in classical physics too. You could, there's nothing to prevent you from imagining that you could identify some sort of vector with the two configurations of heads and tails, but it wouldn't do you any good. There'd be no particular purpose in doing so. In particular, what sense would it make to add the two vectors heads plus tails? Sure, you can call the configuration heads by the label, if you like, a ket vector with an h stuck in it, and just call it that. You could call the down state or the tail state t, but you would have no meaning whatever to a combination like, oh, I don't know, again, complex numbers, alpha times heads plus beta times tails. What on earth would that mean, in particular with alpha and beta being complex numbers? Doesn't mean anything in classical physics. So this is something you would not entertain, adding the two vectors together. And therefore, since you wouldn't entertain the idea of adding them together, there's no point in calling it a vector space. Instead, you just call it a set, heads and tails, and you never think about combining them together by the operation of addition. The operation of addition has no meaning for points in a set. Of course, you can form the union of 2 points, but that's not adding the 2 points together to form a third point, so to speak. You don't add 2 points together in a vector space to form a third point, but you do add 2 vectors together to form a third vector. So there must be some kind of concept of a state of this two-level system, of this two-state system, which is the linear superposition of 2 of them. That's what's new in quantum mechanics, that this has the meaning, this has a meaning, and it has a meaning of a particular state of the heads-tails system, which is different than either heads or tails. What way it's different, how it's different, is at the heart of quantum mechanics. This is going to take us a little bit of time. We're probably not going to really get to it tonight, but that's the basic setup, that the states of a system are vectors, and not only that, that we can add them together and make sense out of new states, which is, for example, a linear combination of heads and tails. It's neither heads nor tails, but it's some number alpha h times heads plus alpha t times tails. Now, and if there's no reason to restrict ourselves incidentally to 2 states, but before I go on to more states, 6-state system or a 10-state system, let's just specify a little more carefully the properties of the vectors heads and tails, or the properties of the vectors 1 and -1. First of all, they are orthogonal to each other. Now, this is a postulate. The postulate is that states of a system which are clearly distinguishable by a single experiment, and in this case the experiment would simply be to look, is it heads or tails? One experiment. If by, by a simple experiment you can uniquely distinguish the 2 configurations, then the vectors that go along with those 2 configurations are orthogonal. So orthogonal vectors correspond to configurations for which there is an experiment, a clean, simple experiment, that can tell you whether it's one or the other. That's the meaning of orthogonality. Distinguishable in the sense that there's an experiment that can distinguish them. Okay? Good. That's number 1. So we assume that h and t are orthogonal to each other. That means that h and t have 0 inner product. Another rule, which is now somewhat arbitrary, but we can impose it, we can also choose the vectors h and t to be of unit length. So let's also choose h equals tt equals 1. In other words, the 2 vectors h and t form a basis. A basis identified with the distinguishable states of a system which can be distinguished by a clean experiment. Right? We identify the different configurations that we can measure with a basis of in the vector space. Nothing special about two vectors. Another simple system would be the die. Die as in dice. We throw a die. It comes up with anything from 1 to 6. 1, 2, 1, 2, 3. This corresponds, it's on the table. We identify this with the state. Let's call it now, just call it 3. This doesn't mean its length. This doesn't mean the length of the vector is 3. It just means the vector is called 3. There are 6 of them. 6 distinct, 1, dot, 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 up to 6. Here, the state vector space was two-dimensional, 2 basis vectors. Here, the state vector space is 6-dimensional. 6 orthogonal vectors, all mutually orthogonal. I'm not going to write that down. All mutually orthogonal and of unit length. In other words, the 6 vectors corresponding to the 6 distinct configurations of the die, distinguishable configurations, that you can tell the difference between, basically in a single experiment. Just one experiment, you just look at it and you see which face is up. That determines for you which of the 6 vectors describe the particular configuration. Now, I haven't told you the physical meaning of adding these vectors together. I just told you, though, that it makes sense in quantum mechanics to do something you would never do in classical mechanics, and that's add these 2 configurations to find yet some new configuration which is different than either of these, H and T. That's what's new in quantum mechanics, that if you had a single coin, which whenever you measured it was either heads or tails, there are additional possibilities which are somehow mixtures of heads and tails in a way that doesn't happen in classical physics. The same thing is true here for the die. You can have, let's give them coefficients again. This would be alpha 1, 1, plus alpha 2, 2, dot, 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 up to alpha 6, 6. This is some state of the die which doesn't have a classical analog. Well, what does it mean? We're going to eventually get around to exactly what it means, but let me tell you some properties of such a state. Let's begin with the heads and tails. Whenever I look at a coin and I check whether it's heads or tails, I find it's either heads or tails. I don't find, I mean, except with the extremely unlucky situation, or maybe lucky situation where I can't even get it to stand on, and no way I can do it. It's either heads or tails. If I check whether it's heads or tails, it will be one or the other. All right, so if I check, it's one or the other. What kind of thing is alpha h heads plus alpha tails tail? It is a state, and it's a state which, if you measure the heads or tailsness of it, will have a probability of having heads and tails, and the probabilities for heads and tails will be related to alpha h and alpha t. All right, so this is some state in which, when we look at the penny, it has a probability for being heads and a probability for being tails. Remember, quantum mechanics is probabilistic in a way that classical physics is not. All right. So what is the probability for heads? Let's call it P sub h. That's the probability for heads. It has to be positive. It has to be real. These alphas are arbitrary complex numbers. What can it be? It's just alpha h star alpha h. That's a postulate of quantum mechanics, and of course the success of this postulate is an experimental fact, but it's a postulate of quantum mechanics, if we take a sort of axiomatic view of it, that the probability for heads in this case would be alpha h star alpha h, which is a positive real number. And what about t? The probability for tails would be alpha star t alpha t. Well, that tells us one more constraint about these vectors describing physical states. We do expect the probability for H plus the probability for T to add up to 1. So we expect then that alpha H star alpha H plus alpha T star alpha T is equal to 1. Let's give this vector a name. I don't know what to call it. Let's just call it, anybody have a suggestion what I should call it? B? P. Why P? Well, this isn't the probability. This is some vector. Here are the probabilities. I don't want to call a vector. I don't want to call a vector by a name which stands for probability. Let's just call it V for vector. Coin. Okay. Confused coin. How about confused coin? CC. Confused coin. Coin doesn't know whether it's heads or tails. It's got some probability amplitude. These are called probability amplitudes. These are complex numbers. They can be positive, negative, or complex, imaginary, whatever you like. And when you add these together, you get a coin, a state of a coin, a state of a coin. You don't get a coin, you get the state of a coin, in which somehow it doesn't know, or it's, if you measure it, you will find with probability alpha H star that it's heads, and similarly for tails. All right. This object here is just the inner product of the vector CC with itself. It's just alpha H star alpha H plus alpha T star alpha T. So this is just the inner product of the vector with itself. CC does not stand for cosmological constant, and it doesn't stand for, what is it that you do when you send an email message? You carbon copy it, I guess. It's not carbon copy, it just stands for confused coin. All right. Any state, any properly defined state of the confused coin should have unit length, should be normalized. That's another postulate of quantum mechanics, that the properly defined states of a system are normalized, have unit length in the sense that their inner product with themselves is equal to 1. That's the statement that all probabilities should add up to 1. Likewise, for the die, we have alpha 1 star plus alpha 2 star, that is equal to 1. And if we call the state now, I guess we should call it CD for confused die, then its inner product with itself is also equal to 1. So that's another postulate of quantum mechanics. The first postulate is that states which are distinguishable, clearly physically different, because you can do a measurement to distinguish them, correspond to orthogonal vectors. Second statement is that all of the linear superpositions which correspond to physically sensible states should have unit length, should themselves be of unit length. The basis vectors are of unit length, but we should also only consider states whose total normalization is equal to 1. Those are postulates of quantum mechanics.
Yeah, I kind of lost you there. Alpha H and alpha T, how did they become?
You lost me or I lost you?
Well, I don't know. Yeah, so alpha H and alpha T,
yeah.
they became probabilities at one point. Can you explain that a bit more?
That is a postulate of quantum mechanics that, if you like, that's the meaning of the alphas, but it's not the total meaning of alphas. There's more to the alphas than just probabilities. But as I said, it's a postulate of quantum mechanics that the states of a system form a vector space. If they form a vector space, we can add them. We have to then interpret, we have to know what the meaning, what the physical meaning is of a superposition of states like that. I'm not telling you the full meaning. I'm telling you now one feature of such states. We will learn more about these and we'll get familiar with the idea. But for the moment, one of the postulates is that the probabilities are simply the squares or the absolute values of these probability amplitudes. Not the absolute values, the square of the absolute values of the probability amplitudes. It's only possible to justify these things by showing you how they work, by showing you the ins and outs of it and how they work and how they lead to a consistent picture. It's best at this point to accept, make sure you know what I'm saying. The words, I think, are clear, that the probability, if this is the state of a confused coin, then if somebody somehow created a coin confused in this exact fashion, what does it mean for the probabilities to be this, incidentally? What it really means is that you have a lot of these confused coins all created the same way. Let's be very specific now. We have a lot of coins, 1 million of them. And we have a lot of coin tossers, and they all toss the coin, or they all do the experiment, whatever that experiment is. It's not really tossing coins. There's something else that we're going to do. But we do some experiment starting with all the coins the same. Let's say we take all the coins and put them heads. And then we do something to that coin, whatever it is. We put it in a magnetic field. We turn the magnetic field. We do various things to it. But not just with one coin, but with a whole bunch of them, each one dealt with identically to the others. A zillion of them, however many we need in order to be able to use the statistics and probability in a sensible way. Then, after having done this, we look at the coins. I look at the first one, heads. I look at the second one, tails. I look at the third one, heads. Tails, tails, heads, tails, heads, and so forth. All right? From the frequency of heads and tails, I can experimentally determine the probability for heads and tails. If I have equal number of heads and tails, the probability is 1/2. If 3/4 of them are heads and 1/4 are tails, and I have enough of them, then I say the probability is 3/4 heads, 1/4 tails, and so forth. The postulate is that the probability for heads and tails is given by these coefficients here. That, as I said, is a postulate. You can't ask me why. You can't ask why a postulate is true. Of course, you can ask what the experiments which led to this weird guess were, but we only have 10 weeks, so we've already gone through 2 of them. Yeah.
I was just wondering, does that mean then that like alpha h and alpha t are equal to like 1/√2?
Well, that would be the case. That could be, well, they can be complex numbers, yeah. But that would be in the case of equal probabilities, yeah. Well, it doesn't have to be 1/√2. It has to be a number of length 1 times the 1/√2. But you've got the right idea, yeah. Remember, they can be complex numbers. And there are complex numbers whose length is 1. Any number, whoops, any complex number which lies on the unit circle is a number whose length is 1. All right, z star z is equal to 1. All right, so if I choose these numbers to be unit numbers divided by the square root of 2, then we would have the probabilities adding up to 1, each probability being 1/2, yeah. So yes, you've got the right idea. Okay. But do keep in mind that in general, these are complex numbers. For the die, we would put a 1/√6 in front of it to do the same thing. Now, what I haven't told you is it's pretty obvious in classical physics how you make a heads or a tails. You just flip the coin and slap it down and see the heads or tails. How do you construct for a coin one of these weird states, which is half heads and half tails? That I haven't told you how to do it experimentally. We're going to come back to that. We were not going to deal with coins, of course. We're going to deal with electrons. But for now, we want to get some formal ideas. We want to get to the quantum mechanics as fast as possible. And to get to it as fast as possible, it's best to just tell you what the postulates are and then show you how they work. Show you how they work, and then come back and say, how the hell did anybody figure this out? Where did it come from? What were the experiments that led to it? The orthogonality of those states which correspond to measurably different configurations in a single measurement, okay? Let's be very clear about it. Yeah. Right. This is a is it a necessity? Well, you'd run into bad things if you didn't do it. The quantum mechanics would fall on its face very quickly, but let's do it, and then we can come back and ask what would go wrong if we didn't do it. Given the shortness of the time that we have available, I think the best way to do it is to give you a bunch of postulates, show you how they work, and then come back and say what would happen if we did something else. And rather than to try to derive these ideas. In fact, even if I had 30 weeks, I would probably do it the same way. Well, I actually think I'm finished with the things in my notes. So no, I'm not. No, I'm not. I'm not at all finished with the things in my notes. But I don't know. Have I saturated you thoroughly? No? Okay, we can go on a little bit. All right. The next subject is next subject, mathematical subject, before we go on to its physical interpretation, is the concept of operators. Operators are operations that you do on vectors. Let me give you some examples from ordinary vector spaces, from the kind of vectors that you draw on the blackboard. There are operators and there are operations. Operators are a special case of operations, or really strictly speaking, one should speak about linear operators. Linear operators are a special case of operations that you can do on vectors. Here's an operation that you can do on vectors. I just draw this to make some axes. Take all of the vectors. Incidentally, when I speak of operations you can do on a vector, I mean operations that you do on all the vectors in the vector space. All right, so here's an operation I could do. I could rotate all of the vectors by the same angle. Every vector in the vector space rotate by 90 degrees. That would mean that this vector would go to this vector. I wish I had some more colors. Well, the other colors don't show up very well, so I'll use wiggly lines. Wiggly line, this vector would go to this vector, and so forth. Rotation by any angle is it's clearly an operation that I can do on the vector space. It is also a linear operator. We'll define linear operator soon enough. Let me give you another example. I could keep the direction of the vectors fixed and double the length of every vector. That's an operation. It would take every vector and simply double it. In fact, that's just multiplying it by a number. So multiplying vectors by numbers is also an operator. An operation, and they're also linear operators, but we'll come to linear operators soon enough. Take every vector and reflect it. Reflect it about the x-axis. So take this vector and replace it by this vector. That's an operation that you can do on the vector space. Every vector goes to some unique new vector. That's also a linear operator. Let me give you an example of an operation which is not a linear operation. Take a vector and square its length. If its length is 2, replace it by a vector of length 4. If its length is 3, replace it by a vector of length 9. That's not a linear operation. It's an operation, but it's not a linear operation. So what does it mean? What does the notion of a linear operator mean? What does it entail? Okay, so two things, and we've already used these things over and over, but let me spell it out. An operator is a linear operator, and I'll represent linear operators by letters with little hats on top of them. That's a somewhat standard notation. Often operators are represented by boldface, but I can't do boldface on the blackboard. So I'll use the little hat notation. An operator is indicated by a hat on top of it. This is not a bra symbol turned on its side or a ket symbol turned on its side. It's just a little hat on top. Indicates operator, linear operator. A linear operator has the property that if it acts on any vector, it gives another vector. So it gives a kind of image vector whenever the linear operation acts on it. All right? If it acts on a vector, take a vector which is alpha times a. Remember, vectors are things you can multiply by numbers. Multiply the vector a by a number, and then apply the linear operator. Well, the answer is equal to alpha times the linear operator on a. So in other words, it just says that if you take twice a vector and apply the linear operator, it just gives you twice what the linear operator gives on the original vector. Was that clear? Did I say that clearly? I hope so. Okay. So that's one property of linear operators, that if you multiply a vector by a number and then operate with the linear operator, it just gives you the number times the linear operator on the original vector, number one. And number two, a linear operator, if it acts on the sum of two vectors, just gives you the sum of the action on each of the vectors separately. So it gives you L times A plus L times B. Times being used in the sense to mean operating on. Let's just check that for some simple operations. If I take a vector, if my operation is rotation by 90 degrees, let that be the operation for the moment. Is it a linear operator? We want to check it. Well, the first question is, supposing I take a vector and I multiply it by a number. Let's say double it. Do I just get twice what I would get if I rotated the vector, the original vector? So here's the original vector. Here's twice the original vector. The operation is rotation. It rotates every vector by 90 degrees, let's say. In particular, the result of rotating twice A is the same as twice the result of rotating A. That's obvious. All right? So it satisfies the first rule that if I rotate alpha times a vector, I just get alpha times the rotated vector. What if I rotate the sum of two vectors? If I rotate the sum of two vectors, here's two vectors, in ordinary vectors, A and B. The sum of A and B is just the resultant, like that. If I rotate A and B, the whole parallelogram rotates, and A and B will rotate, but so will the sum of A and B rotate. And so the rotation of the sum of A and B is just the sum of the rotation of A and B. And so it satisfies this rule here. You can check that. Check that for yourself. Multiplying a vector by the number 2, again, is a linear operation. But squaring the length of a vector is not. Check that out, and you'll discover that that's not a linear operator. So there's the notion of linear operators, and here's its definition. Okay. Linear operators are important. They don't correspond to states. They correspond to the quantities that you can measure. They're called observables. Observables means the things that you can measure. You can measure the headsness or tailsness of a coin. So the headsness or tailsness of the coin is represented by a linear operator. I think we have to finish now. We'll come back to this next time, and I'll explain to you how the observables that you measure are identified as linear operators in quantum mechanics. And then we can do some little examples and work out some predictions that would follow from this set of rules. The set of rules seems very abstract, but we're almost at the stage where we can make predictions about coins based on quantum mechanics by using this set of postulates. We're fairly close to that by now.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.